Okay, we can finish up here and kind of continue on. So we've been talking about ways to classify eruptions. And this last wave is looking at explosive versus effusive. In order to continue on talking about explosive eruptions, introduce a term to you. You've probably seen this already, maybe not, but the term tephra is something we'll use a lot when we talk about explosive eruptions, and it refers to the material that's produced by these explosions, the fragmental material. So it's the broken magma that is ejected during an eruption, and it can range in size from sand size and smaller, which we call ash. Lapilli is sort of pea-size ash, and typically it's something called accretionary lapilli. This is a term that comes from deposits produced by the volcano Vulcano in Italy. Lapilli is an Italian term, and if you look at it, it's sort of pea-sized, but what it is it's like an ash ball. It's a conglomeration of ash that is stuck to other ash. That's why they call it accretionary lapilli. It looks like, I don't know if you've seen grapple or corn snow. That's exactly what it looks like. And it's kind of put together the same way, where it's adherence of ash to other ash, typically by having a little bit of steam present. And volcano is famous for its volcanian eruptions, which we're going to talk about here in just a minute, and it tends to produce lapilli. You can get pumice that ranges in size from hand size up to pretty good boulder size, up to a cubic meter or more. And then blocks and bombs. Blocks are the solid chunks that are tossed out. They can be the size of a house or more, like this one in the lower right. Or you can get bombs, which erupt soft. They're still molten. And they take on a more fluid appearance, like the one in the lower left. So ash, lapilli, blocks, bombs, all are considered tephra. And as we'll see, probably not this class, but in a future class, we can use different sizes and amounts of tephra to classify different eruptions as well. So this is something we'll be returning to a little bit today, but more in future classes. And yeah, I don't know. I'll have to take a look. Yeah, my guess is it's a big piece of red scoria. I don't know exactly the one. And yeah, that's probably coming out of an explosive basaltic cone. And some of them can be pretty big. I mean, I've seen blocks size of this room that have been ejected by eruptions that you wouldn't consider to even be that big. You know, you look at them from a distance, they don't look that big, and then you see these gigantic pieces that have been tossed out. It's really pretty impressive. But a volcano like St. Helens, which is kind of a moderate size eruption, there were blocks the size of this room that were tossed almost 20 miles. So again, that's like from here to the interstate. You can do you can go do the simple physics ballistic problem and try to figure out how much energy is required to throw a rock that size that far, and it's really ridiculous. So the other end of this third classification scheme, effusive explosive, is the effusive part, which is the lava flows. When you don't have enough volatiles or sticky enough magma to create the fragmentation of magma, stuff tends to just run out onto the Earth's surface. A lot of times this will happen after an early phase of explosive activity. It's really common for volcanoes to go through an early explosive phase and sort of blow off all the excess volatiles. And then the remaining magma is a little lower in dissolved volatiles and won't have, you can think of it as the propellant for the explosions. and the stuff just sort of bubbles passively to the surface. You also tend to get more lava flows in submarine environments because the pressure is higher. The pressure keeps more of the volatiles in solution, so you get less bubble growth and less explosions. Lava flows have always kind of been my deal. That's what I've spent most of my career studying. I've always enjoyed it, and I've always tried, when you spend your life studying something, it's hard not to think about why. It's like, why am I interested in this more than explosions or more than sedimentary rocks, God forbid, or more than anything else? And I think it's because, in geology, we're used to things happening so slow you can't see it on a human time scale. And volcanoes, earthquakes, landslide, that's change you can see on your time scale. And to me, that's a time scale and a size scale. I like to be able to see things that I can see. I don't like microscopic crap. So it's the right scale physically, and it's the right time scale for me. So here's some basaltic lava from Hawaii. I'll just let it play. You can watch it. If you have questions, just shout it out.
You're still fall asleep to the lava. Get the right music set to that. Totally relax.
Did you notice right near the end, those lava flows had a dark streak down the middle? Go back. I'll see if I can. Right. Missed it. There. See how they all have a dark streak down the middle? They're trying to crust over. I mean, this is material that's losing its heat so rapidly that it's trying to form a upper crust of rock. But because it's flowing downhill, the edges are continually broken up through shear along the edge, where right along it's moving super slow, and out in the middle it's moving fast, and in between there's sort of a speed gradient, and it just sort of tears the magma up. When you get to the middle, this is all moving the same speed. It's more or less moving like a plug down the middle, and it's able to start cooling. So it's not unusual to see those sort of dark, cooled lines, and that's just on the surface itself. The other thing, too, which is fun if you ever get to go, is try to throw a big rock in this stuff. I've done that a lot of times where I'll take the biggest rock I can pick up, 30, 40 pounds, right, and actually give it a throw and throw it at the magma. And what do you think it does when it actually hits that lava? It just sort of thuds on the surface. Some people think, oh, if you throw it hard enough, it's going to make the lava splash up. Never does that. And it's because of the stuff we talked about the last couple of weeks. It's too viscous to move out of the way of the big rock going in. So the rock doesn't actually penetrate very far, and it has a yield strength. Actually, if you throw a small rock at it really hard, it'll just bounce off the surface because it won't exceed the yield strength of that material. It's the weirdest thing. Yeah, you can chuck rocks at this. I love throwing stuff in lava. I don't think Pele likes it, but I hope she understands that I find it really cool and I learn from it. So let's see what else. I think I have one more here. Oh, yeah, let's try this. So this is an flow. And they move pretty slow. Some of these will move at a walking speed, but this is pretty typical. If you stay there long enough, you'll see the whole flow move. And this flow is coming out over the top of Pahoehoe flows, which is that ropey, more fluid-looking morphology that you get next to it. But if you give this a whole day, it's going to move 100, 200 meters. And for the residents who are trying to protect their homes and putting up berms and stuff, flows to sort of just steamroll through whatever they come in contact with. The more fluid Pahoehoe will move around obstacles. This big mass of just plows its way forward. Yeah. Yep. So yeah, this material, this material down here, exactly the same chemical. Exactly. There's no difference. It all has to do with the speed at which it's coming out of the ground. Or moving across the surface. You tend to get on steep slopes where the stuff's moving faster. We'll talk about Pahoehoe and a lot in a couple weeks. Yeah, it really tried too. That's a tough environment to have grown that big in, and then just to be unceremoniously stomped out by the flow. It just doesn't seem fair. So yeah, everything you can see all the way in the background, it all formed by this same process, the slow march forward of this lava and create these giant volcanoes, these giant islands. If given enough. This is flowing. Yeah, the actual vent is about 10 miles away. Yeah, that's sad. Happens to people's homes too. They can just see this. They just inches closer and closer and closer to their homes, and there's no stopping it. YouTube's ads got. Let's go back. YouTube, yeah, it's kind of frustrating now. Okay, let's see what else we got. Okay, let's try this again. So products of effusive volcanism, really you have three types. You have lava flows, like we just saw in the previous video. You have lava domes. I don't have any dome footage today, but we'll watch some in a few weeks. And then coulees, which are kind of a hybrid between lava flows and domes. They're flat top like lava flows, but thick like lava domes. This term here, rheology, is basically the study of fluids and fluid properties such as viscosity and yield strength. So when we talk about viscosity and yield strength, we're talking about the rheology of the lava or magma. And depending on what your rheology is, your yield strength and your viscosity can give you lava flows that look really different. When you have things that have a real high yield strength, remember, high yield strength leads to lava flows that are really thick. It can support all the weight of the overlying material. Then you get things like domes and coulees. If your yield strength is really low, you tend to get thin flows that have aspect ratios, thickness to area, that are extremely small. Coulees are a little thicker and a little shorter, so their aspect ratio is a little bigger. And then lava domes are very short, stubby, but very tall. So you can actually look at the thickness to length ratios on lava flows and get an idea of what their fluid properties are. And then, as we've talked about earlier, fluid properties are related to composition. Basalts tend to have low yield strengths, low viscosities, and tend to form lava flows that are long and thin. Rhyolites have a really high viscosity, real high yield strength, so they don't flow far, and they're really thick, so you have a really high aspect ratio. So domes tend to be rhyolite, dacite sometimes. And then you have coulees, which are kind of in the middle. They're thick, but they flow a little bit. So they have moderate viscosities, fairly high yield strengths. Lots of andesites and dacites fall into that range, but some rhyolites as well. So this is sort of a first order approximation for looking at flows that you actually can't physically get to. Flows on other planets, flows on environments that don't allow people to get close to. So just looking at the aspect ratio, length to thickness, gives you an idea of what kind of composition that lava flow or dome or coulee might be. So we'll come back to this a little bit later, but I just wanted to introduce this to you today. All right, any questions so far? All right, so we have a couple of classification schemes, one based on location, subaerial, submarine, subglacial, planetary. We have another one based on the type of vent, summit vent, flank vent. We have another classification scheme based on activity, explosive versus effusive. And all those work, but this final classification scheme is the one we use the most. And it's based on type eruptions. Type eruptions or famous eruptions. You know how in stratigraphy we have type locality? It's a location where a sedimentary rock is exposed that's particularly good. So we have the Morrison Formation, which is particularly well exposed near Morrison. Well, for volcanoes, we do something similar. We know Hawaii erupts in a very classic, repeatable pattern. So we have Hawaiian type eruptions. Vulcano in Italy erupts very consistently, very similarly, but very differently than Hawaii. So that's a different type of eruption. Now, depending on which volcanologist you talk to, there might be 6 or 8 different type locations. We're going to get into some of those today. And then what you'll see is that as a new volcano or different volcano pop up, it might exhibit Hawaiian type eruption characteristics or Vulcanian type eruption characteristics or Plinian eruption characteristics. Ultraplinian. Now, it's possible for Hawaii to have eruptions that aren't Hawaiian. Sometimes you get explosions in Hawaii, and some of them are volcanic in nature. So you can have volcanic eruptions in Hawaii. You can have Hawaiian eruptions at Mount Etna. It simply refers to a type of activity that's tied to a particular volcano or location. Some of the things we look at are if it's explosive, how tall is the column height? How high above the ground is material ejected? Hawaiian eruptions tend to be low columns or no columns. Ultraplinian can go up to 100,000 feet or more. Composition of magma, we know that Hawaiian eruptions form where we have basalts. Plinian and ultraplinian are where we have far more silicic materials. Type of conduit, we know Hawaii is fed by fissures, cracks in the ground, rather than a large magma chamber and central conduit like you might get for a Plinian eruption. Plinian eruption could also be called a Vesuvian eruption. It's named for the AD 79 eruption at Mount Vesuvius that was witnessed by Pliny the Younger. Pliny the Elder, another philosopher, was actually killed in that eruption. So rather than call it Vesuvian, they call it Plinian for the Pliny family that not only witnessed it, but one of the family members died in it. Size of the tephra that comes out. Volcanic eruptions are famous for ejecting blocks and bombs that can fly several hundred meters to a kilometer. Ultraplinian eruptions are so explosive that they actually fragment material into almost dust. So you typically just get really fine ash because the eruptions are so powerful that it just pulverizes everything into the smallest pieces. Shape of the tephra. Hawaii, the material is fairly coarse and still fluid when it's ejected, so it tends to splat on the ground. Sometimes they call it cow dung bombs. And then ultraplinian is just like I said, it's basically dust because the eruptions are so powerful. You saw in that one of the explosive videos from Iceland, you see all the lightning? That's from all the fine ash. It's been pulverized so small and it's constantly slamming in that it's producing a ridiculous amount of static electricity. And then every once in a while it congeals and forms these lightning bolts. So it can create its own lightning if there's enough fragmentation of this material. So you tend to get really fine fragmented ash when you get some of this lightning produced in eruptions. Where there's water present, water increases the explosivity in many cases and increases the fragmentation of material, making it smaller. So all of these things are used to be used as descriptors when we look at these classic eruptions. So we'll only have time probably to do the Hawaiian one today, and then we'll talk about the others after the test in a couple weeks. So Hawaiian eruptions typically have low columns when they first start. Most Hawaiian eruptions start out with what's called a curtain of fire because Hawaiian eruptions usually take place along rift zones, which are just cracks that extend up to the Earth's surface. This material tends to come out along a crack. And it's initially jetted up to a few hundred meters, maybe a kilometer, along a length of this crack, so it looks like a big red curtain. But that's not the most thermally efficient way for an eruption to proceed, where you have a large surface area that can lose heat. So what happens after the initial curtain of fire is that the eruption will localize down to one vent. So it starts out along a rift, and then it localizes to an event, And sometimes at the vent, then, all of the eruption fury is targeted at this vent, and that can make the column height actually grow. But typically, these are pretty low columns. They're typically basalt, very fluid material. Gases are escaping readily in this material, but if it can't escape enough before the eruption happens, then you tend to get these low columns of explosive material. Eventually, the volatiles will bleed off the top of this magma body and will be followed by lava flows. So it starts out as a curtain of fire, localizes down to a vent that's producing a low column material, and eventually then the material just oozes out of the ground rather than forming any column at all. And I'll show you some photos of this here in a second. Strombolian is similar. It's the next stage up. So it's slightly higher columns. It's more explosive than effusive. You don't get much lava flow production in Strombolian eruptions. They tend to be sort of pulsating, basaltic, low columns. Hawaiian's a little different. You tend to get this curtain of fire, a small little vent that'll jet material up, and then that will slowly wane, and then stuff just oozes out on the ground for days, weeks, years, or in the last case, decades. So yeah, Strombolian is actually sort of the next step up from this. It is a type of eruption. Yeah, we're going to talk about it in a couple weeks. I'm not going to get to it today, but it's next on my notes here. Yeah, you tend to go Hawaiian, which is sort of the lowest explosive phase, then Strombolian, then Vulcanian, then Plinian, then Ultraplinian. And then we have Surtsian, which is mixtures with water. But yeah, all of those are famous types because Stromboli, you go there, it's always erupting the same way. It doesn't do anything different. You know, you go there and it's just blast after blast after blast after blast. It just goes on all day long. Hawaii, you get these curtains of fire, low jets, and then lots of lava flows. Now, most of the eruption in Hawaii is going to be lava flow phase, but during the early explosive phase, you tend to get material that's still fluid. So you get bombs, or you get these cinder size, and you've probably seen cinders that are a little smaller than baseballs, golf ball size. And sometimes cinder cones form in these eruptions, but not always. These are typically just fed by the volatiles that come out of solution. You don't get a lot of meteoric water interacting with this material in Hawaii, except where it enters the ocean. Sometimes when lava enters the ocean, you can get a significant amount of seawater that comes in, and you get lava flows that essentially explode in the presence of seawater. And they form these sort of cone-shaped constructs right on the edge of the ocean called littoral cones. I got to see one of these form about 20 years ago, and it was one of the neatest eruptions I've ever seen. It was at night, and it was just exploding out of the ocean. Pretty spectacular. But you have to have just the right amount of lava going into just the right depth of water to make these happen, and it doesn't always occur. So I think I have some images of this. So this is the curtain of fire. So there's a rift underneath that, and the lava's coming up. But because it's kind of a planar tabular body, it loses heat fast. So it starts to localize into vents. And you can see that there are like little fingers sticking up where, say, this area right here, coming out of the ground a little more vigorously than right there. And what'll happen is it'll sort of localize down to a couple active vents, and then whichever vent seems to have the clearest path to the surface, it'll eventually, that one will take over and all the material will move through it. But at first, there's so much material and so many volatiles that it sort of overwhelms the system. And sometimes this can occur over several kilometers. The one in 1984 on Mauna Loa, which is actually here in the background, there were several miles of curtain of fire that popped up along the rift zone up in here. And then it localized down to a single event and then sent lava flows down to Hilo. And the lava flows poured right to the edge of Hilo and then stopped. So people in town were pretty petrified that it was just going to overwhelm the whole city. This is a view from above. You can see it's starting to localize down into lots of separate little vents. And then one of these, whichever is the most powerful, maybe this one right here, that'll be the site where most of the material will continue to pour through. Yeah? Yeah, yeah. If you think about this as coming up from below, it's going to have like, at first it's going to be a wedge of material that comes up, okay? But then, because that's not thermally efficient, it's going to try to localize down into a cylinder. At first it's many cylinders, so it starts to look like fingers poking up, and that's what you're seeing here. And that's kind of what boudinage is too, is an instability that forms these little cylindrical pipes. So they're not exactly the same, but there's some similarity in the process between them. So yeah. And then it localizes down into a vent. And when it localizes to a vent, it's kind of like a hose. You put your finger over the hose and it goes a little higher. Here you're restricting the opening. It was originally this big rift zone. Now it's being localized to a single vent. And for a while, these material can be jetted up pretty high. This is probably 250, 300 feet. It can go up 1,000 feet or more. Highest ever recorded in Hawaii is 5,000 feet, which is a mile. But that happened as a bunch of material sort of sloughed off into the cone and really restricted it. If you've ever done that with a hose, try to get it to go farther, you make the opening a little smaller. That's kind of what happened there. It was only a temporary thing though. And then this is what happens when some of the lava flows interact with seawater along the coast. You can get explosions. Sometimes you just get pillows. You got to have the right ratio of water depth, and speed of material coming out to make these small explosions. But when they happen, they're pretty impressive, and they can create some pretty big cones. If you've been to Diamond Head on Oahu, that is actually one of these cones that form right on the coast. So that is a Hawaiian eruption, and we're out of time, so I think I'm going to stop there. If you guys have questions, I'll hang around for a few minutes and answer anything that you have. We'll have our test in 2 weeks. No class next week, but if you need to get a hold of me, just email me and we can discuss any questions you have that way.